Today's notes say that we are going to graph logarithmic functions without a graphing calculator, but technically we're still going to use the graphing calculator to help us, so it's kind of lying, but that's okay. So this equation y equals the log base b of x minus h plus k has some characteristics that we need to talk about. The first thing is that there's an error in here, so cross out x equals k because that is most definitely wrong. The graph has an asymptote at x equals h. It is a vertical asymptote. The domain can be found by solving the inequality x minus h is greater than 0, or the easier way to think of it is your domain is x is greater than your asymptote. The only time your domain really changes is if you have a horizontal reflection. If you reflect over the y-axis, that would make it x's less than. But as long as there's no crazy reflections, your domain is x is greater than your asymptote. The range will now be all real numbers. Which we use the word all, and then a capital R with a double stem represents the word real numbers. To graph, we're going to use a table of 3 values. We are going to have the graphing calculator help us find those 3 values. Now, some of you have an older graphing calculator that doesn't have the log base whatever feature. If you ever are trying to use a calculator that doesn't have that feature, or a scientific calculator that definitely doesn't have that feature, you can use the change of base formula. The change of base formula says if you have log base c of u, you do log button of u divided by log button of c. It's called the change of base because you are changing it to base 10. So instead of base c, it's going to be base 10. For example, log base 6 of 15. On my calculator, I'm going to use our fancy feature to show you what log base 6 of 15 is. So we know that log base 6 of 15 should be 1.51. Now let's use the change of base formula. The change of base formula, we would do log button of 15 divided by log button of 6. You always do the log of the big number divided by the log of the base. So if we try that in our calculator, find your log button. Log button 15, close your parentheses. Divided by log button 6, close your parentheses.
Wow. What's the point of that?
Notice you get the same decimal that we did when we did log base 6 of 15. So if you're working with a calculator that doesn't have that fancy log base whatever feature, you can still do logarithms. So try number 11. We would do log of 7 divided by log of 3. Did you get 1.77? Try number 12 on your own. Okay. Blah, 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 blah. Blah, 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 blah. Okay, pay close attention to the process that I do. I've had some people in my classes doing a completely different process than I did in the notes, and it's telling me that they're really not paying attention to notes, but, you know, it's cool. So, just like we've been doing on all of our other graphs, we are going to use everything up to the x. So, I am going to enter into my calculator y equals log base 2 of x. Now here's the cool thing. If you have one of those older calculators that doesn't have the cool log base whatever feature, you can use the change of base formula for this. So I can punch in log button x divided by log button 2, and I will get the same thing as those of you who do log base 2 of x. So you can use an older graphing calculator for this as long as you're familiar with the change of base. In the table, we are going to pick a couple numbers to graph. So I like the point 1, 0. We can't use the point 0 error because there's no way to graph that. What are some other points that you like in that table? 2, 1 and 4, 2. It will not always work out perfectly. You may have to graph some decimals. Don't shy away from that. You may have to graph some decimals. Now, these are our temporary points. So I'm going to graph these with just a little X symbol. So 1, 0, 2, 1, and 4, 2. Let's talk about how these points are going to move. The -2 and the +3 describes how these points are going to move. What does the -2 tell us? Right 2. And what does the +3 tell us? Up 3. So each of these points has to move right 2 and up 3. Before I actually connect my points, let's think about the asymptote. We have a vertical asymptote, and because the graph moved right 2, the asymptote is also going to move right 2. So I draw in my asymptote to remind me that when I connect these points, I don't want my graph to cross that asymptote. So there's a lot of things to think about. You think about your temporary equation, get your points, move the points, think about your asymptote, connect your dots, and now let's do the part at the bottom. The asymptote moved right 2, so the equation for the asymptote is x equals 2. Anyone want to take a guess on the domain? X is greater than 2. Your domain is x is greater than your asymptote. When would the graph have a domain x is less than? If there was a negative inside the parentheses and it flipped it over the y-axis, if your graph was on this side of the asymptote, then it would be x is less than. But we don't have that, so we can ignore that. Okay? Our range. Anyone want to take a guess on the range? Yes, it is always all real numbers. The square root of -2 is a not real number. The square root of negative numbers are not real numbers. Number 2, again, we are going to do everything up to the x. So keep everything up until the x. Y equals log base 5 of x. That's what I'm going to plug into my graphing calculator to get my temporary points. Again, if you do not have the fancy new feature, you can use the change of base formula. Log of x divided by log of 5. If you have that fancy base feature, remember it's alpha window, and that pops up that menu, and then option 5 is that base feature. Okay, in the table, we're going to pick some points that we want to graph. We can't do 0 error. I'm going to pick 1, 0. What's the next point that looks good? 5, 1. But do you see how the y values are increasing really, really slowly? So I'm going to use 5, 1 as my third point and then pick something in between, like maybe 3 and 0.7. Really, the points that you choose to graph are entirely your choice. Whichever crazy decimals you want to graph, those are the ones that you can choose. So 1, 0 is a temporary point, and 3.7 and 5, 1. How are each of my temporary points moving? That also means that our asymptote is moving left 1. This is where using different colors or different symbols for your points is really, really helpful so that you don't lose track of what you're doing. And this curves around sharply and doesn't cross that asymptote. What is our asymptote? X equals -1. Our domain is x is greater than -1. All of our points are to the right of that asymptote on the positive side of the asymptote, so all of our x values are bigger than -1. And our range is all real numbers. The asymptote is -1 because we moved the graph left 1. I want you to make the connection between how we move the graph side to side and the asymptote and the domain. Do you see how that number in the parentheses is tied to side movement, which moves the asymptote, which changes the domain? Those things are all linked together.